Hey Chemistry, we are on to a new unit, and this one deals with the subject of equilibrium. So equilibrium is the final state of a chemical reaction in which the concentration of reactants and products remains unchanged. Some chemical reactions run until all the reactant has turned to products. So if we take this reaction down below, we have all reactants at the beginning of the reaction and no products. And the final state, it's all moved from left to right, and there are no reactants at the end of the reaction, and all are products. Reactions that move only from reactants to products are called irreversible reactions and have an arrow pointing from left to right. Most reactions, though, can move both from reactants to products and from products back to reactants. These reactions are called reversible reactions and are shown by a double arrow. So here we begin again with all reactants and no products. But by the final state, the reaction doesn't go all the way to products. Some of it remains as reactants, some of it is turned into products, and there it's found kind of its happy place where it likes to be. It's based on whatever the concentrations and temperatures are, things of that nature, and so that would determine how far the reaction would want to go. Now you could also start with mostly reactants. There you have mostly products. You could start with 90% products and only 10% reactants, but what you would end up with with those same conditions is the same final equilibrium of the reaction, so 25% reactants and 75% products. In the reaction above, it doesn't matter whether the reaction starts with 100% reactants and 0% products, or with 10% reactants and 90% products. It's going to end at the same equilibrium of concentrations of reactants and products. In both cases, the reaction will stop when there are 25% reactants and 75% products. This is the equilibrium for the reaction. A reaction at equilibrium is in a state of dynamic equilibrium. Dynamic equilibrium means that the reaction continues to move back and forth, but it does so at equal rates. So here we have a room, two rooms, one with 12 children in it, room A, and room B has 7 children in it. Now 5 people move from room A to B, and 5 move back from B to A. So now you're back with the same numbers, 12 in room A and 7 in room B. Now 2 move from A to B and 2 move back from B to A. And again, you end up with the same number that you had before. So room A ends up with 12 again and B with 7 again, even though people move back and forth. This is dynamic equilibrium. So they stay at their equilibrium numbers, but it doesn't mean it's exactly the same children. They can move back and forth, but you'll at any time have 12 in room A and 7 in room B. The equation used to measure equilibrium is called the law of mass action. Often we'll simply call it the equilibrium equation. So here's an example of a law of mass action for a hypothetical reaction. So you have 2A plus 3B on the reactant side, and that produces C plus 4D on the product side. The law of mass action for this reaction is Kc, that's called the equilibrium constant, equals C to the first power, D to the fourth power, over A squared, B to the third power. Kc is called the equilibrium constant. The subscript C refers to the equilibrium of a concentration of a solution. So let's examine how this equation is put together. The equilibrium constants have no units of measure. The equation used to measure equilibrium is called the law of mass action. We'll simply call it many times the equilibrium equation. They mean the same thing. So here's an example of the law of mass action for a hypothetical reaction. There it is again, and there you see it written again. So the products are on the top and the reactants are on the bottom. The exponent on the concentration of each substance is the coefficient of that substance in the chemical reaction. So we said that you can't use coefficients for exponents when we did kinetics, when we did a rate law, but you can use the coefficients, and you do use the coefficients as the exponents when you use an equilibrium equation. Generally, the equilibrium constant indicates how far the reaction has moved from reactants to products. So there's the equation. If products are much greater than reactants, then Kc will be large. In other words, the numerator of that equation will be very large if you have mostly products, and the denominator will be relatively small, and so you'll have a large equilibrium constant. Large Kc equals large fraction of products over small fraction of reactants. If reactants are much greater than products, then Kc will be small. So Kc small is a small fraction of products over a large fraction of reactants. So here's a problem, an example problem. A sample of hydrogen and iodine are mixed in a 1 liter vessel at a temperature of 430 degrees centigrade. Once equilibrium is reached, it is determined that 2.5 moles of HI, 0.25 moles of H2, and 0.5 moles of I2 are present. What is the equilibrium constant Kc of the reaction at this temperature? So there's the equation. Now we create a equilibrium equation from that. So the product is on top, HI, and its coefficient is used as the exponent. On the bottom we have H2 and I2. You multiply those two together. Don't add them, you multiply them. And they have a coefficients of 1, so that'll be exponents of 1 on those. So Kc indicates we are dealing with an equilibrium concentration of molar concentration as opposed to, say, pressures. And there's a number of other equilibrium constants that we will be using. So we need molar concentrations for the equation. Since the reaction takes place in a 1 liter vessel, the moles also represents the molarity. In other words, 0.25 molar, 0.25 molar equals 0.25 moles over 1 liter. So here's the same question. So we substitute in the values, 2.5 for HI, 0.25 for H, and 0.5 for I, and you do the math and you get 50. So the equilibrium constant is 50. This means that the numerator containing the products is 50 times greater, roughly speaking, than the denominator containing reactants. It just means the product on the top is 50 times greater than the denominator. Okay, there are several equilibrium constants we will be dealing with in the next few weeks. They are Kc, the equilibrium in a solution measured in molar concentration; Kp, the equilibrium of an equation of gas pressures; Ksp, the equilibrium of a salt or other solid dissolved in a solution. In other words, these would be what we would think of normally as being insoluble solids. Kw, the equilibrium of water used in an acid-base reaction; Ka, the equilibrium of an acid reaction known as the acid dissociation constant; and Kb, the equilibrium of a base reaction known as the base dissociation constant. The small letters are called subscripts. All equilibrium constants K have subscripts. The law of mass action comes from the kinetics rate laws. So if we look at the decomposition reaction of N2O4 decomposing into two NO2 molecules, this is a reversible reaction that can move forward or backwards. Each of these two reactions has its own rate constant. So if we take the forward reaction, you notice we're just using a one-way arrow there. So we're only dealing with the forward, left to right part of that reaction. So the rate is going to be, now this is going back to kinetics, this is the rate law. It's the rate constant for the forward reaction times the reactant, which is N2O4. And then the reverse reaction, you just turn it around, and it's going to have its own rate constant. So rate equals K reverse, NO2 squared. And we're assuming this is an elementary reaction, so you can use the coefficient of NO2 as the exponent. Now these are both elementary reactions, so the coefficients can be used for the exponents. At equilibrium, the rate of the forward reaction must equal the rate of the reverse reaction. Remember dynamic equilibrium. They go back and forth, but they have to go back and forth at equal rates. So if that's true, you can set those two rate laws equal to each other. K reverse of NO2 squared equals K forward of N2O4. Okay, now we're going to do a little bit of algebra. We're going to divide both sides by K reverse and divide both sides by N2O4, and you end up with K forward over K reverse equals NO2 squared over N2O4. That's going to be the equilibrium constant for this solution. So in other words, K forward over K reverse equals capital KC, the equilibrium constant. This means that the equilibrium constant Kc equals the ratio of the rate constants for the forward and the reverse reaction. Remember, the forward reaction is taking it towards products, and the reverse reaction is taking it back towards reactants. The larger the value of K, the more the reaction moves in the direction of products, that is left to right. Large Kc means more of the reactants turn to products. Small Kc means more of the reactants stay as reactants and don't turn to products. Homogeneous equilibrium means that all of the products and reactants are all in the same state. So for example, in this first reaction you see that everything is aqueous. In the second you see everything is gas. That's called a homogeneous equilibrium. We really don't deal with that distinction very much. Whenever a pure solid or a pure liquid or solid appears in the chemical equation, they are not included in the law of mass action, the equilibrium. Now that is important. So pure liquid such as pure water or a solid such as carbon will not appear in the law of mass action, the equilibrium equation. So here we have PbCl2, and we know that from your solubility rules that that's insoluble. But what we're going to learn is it is a little bit insoluble, and that's something called the solubility product. So if a tiny bit of that dissolves, it will dissolve into Pb2 plus ions and 2 Cl minus ions. So the law of mass action is over there on the right. It's the products on top, Pb2 plus, and the Cl minus, and that's squared. Now don't let the ions fool you. They have nothing to do with what we're talking about now, equilibrium. Now you notice that the PbCl2, which is solid, does not appear in the denominator. So PbCl2 does not appear in the law of mass action equation because it is a solid. So here's another example of an acid reaction. Hydrochloric acid plus water will produce hydronium ions, H3O plus, and Cl minus. Okay, so you see everything there is aqueous except water, which is a pure liquid. So H3O plus and Cl minus appear in the numerator because they're products. HCl appears in the denominator because it's a reactant. H2O does not appear in that equation because it is a pure liquid. So H2O liquid does not appear in the law of mass action equation because it is a liquid. Equilibrium constants do not have units. So examples, write the law of mass action for the following reactions. So you can pause when you see each one of these and try to write it. So 2NO plus Cl2 produces 2 NOCl. They're all gases, so they're all going to go in the law of mass action. And it would look like this. Kc equals the product on top, NOCl to the second power because of the coefficient. On the bottom is NO2 squared, and then Cl2, and you do multiply those, you don't add them, you multiply those on the bottom. So here's an ion, cadmium, and 4 bromide ions, and that produces CdBr4 2-. They're all aqueous, means they're in solution. They're not pure liquids, so that means they'll all go in the law of mass action, and that's what that would look like. Okay, next we have AgCl. We know that is an insoluble solid. So that's a solid, and then a little bit dissolves. Again, this is called solubility product, which we'll talk about in a later lesson. So it's Ag plus Cl minus. So they're aqueous, so they're going to go in the numerator, and then the AgCl does not appear in the equilibrium equation because it is a solid. One more, HCl, one we saw earlier. H2O is a liquid, everything else is aqueous, so everything else appears in the law of mass action, and there it is. So let's compare the rate law and the law of mass action, because it's easy to get them confused. Oftentimes students do, because they both involve the letter K. So rate law, again, is kinetics. It's how fast does a reaction take place, and the rate mechanism. Law of mass action is equilibrium. It has nothing to do with how fast. It has to do with how far does a reaction go from reactants to products, or from products back to reactants. Okay, so let's look at the first thing. You can see the rate law on the left. It's rate equals K, A to the X power, B to the Y power. On the right, you see the law of mass action. It uses, the rate law, first of all, does not use the products. It only uses the reactants. And it does not use the coefficients as exponents. Over on the right in red is the equilibrium constant, and it puts the products on top, the reactants on bottom, and it does use the coefficients as exponents. So the purpose of the rate law is to indicate the speed of a reaction. The purpose of the law of mass action is to determine the equilibrium concentrations of reactants and products. Number 2, the rate law contains only reactants. The equilibrium equation contains products in the numerator and reactants in the denominator. Number 3, the exponents are determined experimentally for an overall reaction. And for an equilibrium equation, exponents are the coefficients of each reactant and product, because it consists of two elementary reactions, a forward reaction and a reverse reaction. Number 4, the rate constant is a lowercase k. In the equilibrium equation, the equilibrium constant is an uppercase K and always has a subscript, A, B, C, P, S, P, W, and you'll learn what all those are at a later time. Number 5. The rate constant is part of the rate law equation used to compute the rate of the reaction and appears on the right side of the equation. For the equilibrium equation, the equilibrium constant is the output value of the law of mass action used to determine the equilibrium values of reactants and products, and appears on the left side of the equation. And number 6, units of measurement for the rate constant depend on the order of the reaction. Remember, it could be 1 over S, it could be 1 over ms, various. It changes depending on the order of the reaction. For the equilibrium equation, equilibrium constants do not have any units of measure. So there is a summary, and please study that so that you know the differences. That's simply the summary of the previous 6 slides right there. There are equilibrium constants for equations expressed in terms of gas pressure rather than concentrations. So here is an equation which involves gases, and simply the way you would write it is Kp for pressure, and there you see you'd write P with a subscript of the whatever the reactant or the product is, and then the same thing, you use the coefficient as the exponent. So that's how you would write the law of mass action for a pressure reaction. Okay, using the ideal gas law, PV equals nRT, an equation relating Kp to Kc can be derived. You should know the equation, but not how to derive it. Okay, so there it is. Kp equals Kc times R times T, in parentheses, you multiply those together, and then you raise them to the change in the number of moles. If you go in the other direction, this is simply algebra. Kc equals Kp over the quantity RT raised to the n power, change in number of moles power. So R is 0.0821 liter atmospheres over moles Kelvin. That's the same one you use in PV equals nRT. T is measured in Kelvin. Delta N is the change in the number of moles going from left to right in the reaction. So for the reaction, N2O4 is a reversible reaction to decompose into 2 moles of NO2. And the Kp is 0.256 at 25 degrees. Now, the only thing, the significance of the temperature is you're going to have to convert it. Well, the significance is you're going to have to convert it to Kelvin. So consider the calculation for the conversion of Kp to Kc. So what is the temperature used in the calculation? It's 25 plus 273 equals 298 Kelvin. What is the value of R? There it is. It's the liter atmosphere over mole Kelvin, R constant. What is the value of N? Now, look at the equation. You have 1 mole of N2O4 on the left, and you have 2 moles of NO2 on the right. So the number of moles change from 1 to 2 as you go from left to right, and therefore delta N is positive 1 mole. And what is the value of Kc? Okay, so there it is. There's the formula. You plug in the numbers, verify that you understand those numbers, and that would give you a Kc value of 0.01. Again, no units of measure. Here's another example. A mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at 472 degrees centigrade. The equilibrium mixture of gases was analyzed and found to contain 7.38 atmospheres of H2 and 2.46 atmospheres of N2 and 0.166 atmospheres of NH3. From these data, calculate the equilibrium constant Kp for the reaction. Okay, so there's the equation, and there is how you would write the equilibrium equation there. So NH3 is a product, it's on top, you raise it to the second power because of the coefficient 2, and on the bottom, N2, coefficient of 1 to the first is raises Pn2 to the first power, and 3H2 raises pressure of H2 to the third power, and now it's just plug in the numbers. So there they are. Verify that you understand how those numbers were produced, and you get 2.79 times 10 to the negative fifth for the Kp. An equilibrium constant does not have any units of measure. Equilibrium follows a few basic mathematical rules. Rule 1. When a chemical equation is reversed, the equilibrium constant becomes the reciprocal of the original constant. So let's say we have a fictitious reaction or generic reaction, A plus B produces C, and let's just say the Kc of that is 2. If you reverse the reaction, then the Kc becomes the reciprocal, 1 over 2. In other words, if it's really big going in one direction, it's going to be really small going in the other direction. Okay, next we have rule 2. When a chemical equation is multiplied by a factor, a number, the equilibrium constant is raised to the power of the factor. So example, if the reaction below is multiplied by 2, then the equilibrium constant is raised to the second power. So if A plus B produces C has an equilibrium constant of 3, and then you multiply everything through by 2, then the equilibrium constant is not 2 times 3, it's 3 to the second power, and that would be 9. So you see these rules are not the same as Hess's law, so don't get the two confused. Finally, one more rule. When two equations are added, then the equilibrium constants are multiplied. So if we have A produces B, and that equilibrium constant is 2, and then we have C produces D, and that equilibrium constant is 3, then when you add those two reactions to get A plus C equals B plus D, like you would in Hess's law, but what you get for the K is not the same as Hess's law. You would multiply them together. So 2 times 3 would equal 6. And that takes care of this introduction The equilibrium, again, kinetics, what the unit we finished before deals with how fast a reaction takes place, and equilibrium deals with how far it goes between reactants and products before it finds its happy place and just settles in.